Yes, I can see your screen and I can hear you. Perfect.
Great. All right, let me get started. First, I want to begin by thanking the organizers for inviting me to talk about scalability issues in deep learning. I will quickly jump into the topic. Today, I'm going to talk about the utility bills of deep learning and how to mitigate that. So let me get started. So as we can see, deep learning nowadays is a dominant approach, in many applications. Here, I just gave you a few examples, ranging from computer vision, natural language processing problems, all the way to, drug design and game playing and so forth. And we recently see some very significant trends, in deep learning research. One is the emergence of these so-called all-purpose monster models, which is growing in size very dramatically and in a very fast pace. In the past 3 years, we saw almost 10,000 times increase in the model size in the number of parameters. Right. Another trend often seen in industrial companies which builds deep learning systems is that they stitch together multiple units and components into a big system to do multimodal data processing and many advanced applications. So with these trends emerging, obviously, we are facing growing model complexity, pipeline complexity, data sizes, and modality, and so forth. And they raise a number of challenges in computing and in implementation, which I listed here. Right? We can see that all these applications and the developments requires a lot of computing, a lot of memory and the hardware network bandwidth. It also requires a lot of engineering hours, to develop and debug the system. And also it requires a high skill set from the developers. Just to give you one example, I believe there's now already an arm race between companies to really, obtain or develop, hardwares that is capable to undertake, the very specific and high demanding computing task. Even a modest-sized deep learning model nowadays could use hundreds of hours, using the latest, NVIDIA GPUs. And in fact, the NVIDIA GPUs are also growing, its generations very fast. We are already moving away from A100 to V100, and there are other several, startups developing, a mega scale chips such as the wafer chip from Cerebras, which has, nearly 1 million cores on the chip to allow you computing large models, maybe without using distributed technology, right? So all these actually, requires significant investment from organizations and companies. And also there is a challenge in managing these resources, economically and wisely. So you can see that there is a big utility bill, even going beyond the hardware, right? You need to pay for engineering hours. You need to also pay for electricity, for running the hardware and cooling the hardware. There is also software lifecycle, maintenance. There are also issues on environmental, footprints such as carbohydrate emissions and carbon dioxide emissions, greenhouse emissions, and other things. I guess most of the community in deep learning are not paying too much attention on this utility bill because it is the company or the big players who carry the bill. Researchers usually are not too worried about it, or they choose not to do it if they don't have the resource. And this is not a sustainable way to grow both machine learning and deep learning. So my question is how we can predict and mitigate the cost of deep learning as we see just now. For example, how to effectively train the model, what's the best training strategy, right? How to pick and deploy hardwares to allow training happening efficiently. And how many lines of code, in addition to the model itself, we need to develop, to distribute or deploy the system, right? How to tune the model, and also maybe how to automate composition, parallelization, tuning, and all that, given that we have so many projects and so little time and resource. So toward this cost-conscious deep learning, I'm going to talk a few ideas, that could lead us to think about plausible solutions. So these ideas include how to automatically parallelize machine learning training and inference, how to automatically schedule in training tasks, how to tune big or small models, and also what's the mathematical foundations behind all this. So let me begin by auto-parallelization. As we all know, machine learning and deep learning are largely relying on a type of iterative convergence algorithm, which asks you to update the model parameters iteratively like this until they converge. And the computation of that delta is actually the main task, for every, infrastructure and hardware. When the data become big, you need to sometimes use a technique known as a data parallelism to split the data onto different nodes. Therefore, they can get computed in parallel and then aggregated. If the model becomes too big, you may need to also split the model parameters so that it needs to use a model parallelism technique to distribute the workload. And there has been a number of system artifacts developed, for these kind of applications, such as the parameter server, and also recently more popular, the all-reduce architecture. But on the other hand, behind these two main architectures, there are also a large number of problem-specific artifacts and specific issues that needs to be addressed underlying the problem of computing, memory management, and the communications. Then there is a big space of solutions that needs to be implemented depending on what problem you are solving. Therefore, the existing universe of system artifacts is really bewildering, and it's hard to use and generalize. And that actually is one of the major problem or issue causing deep learning to be difficult, at least at the system and implementation level when they become very big. It is very diverse in terms of the model. Therefore, you cannot oftentimes find a system that can carry different types of a big workload, depending on the model architectures and depending on the models. And here I have a little graph showing you the type of design space people are facing. And secondly, even if you know how to choose, then there are separate code bases and APIs for all these different solutions. Therefore, you need to put a lot of effort in learning them and also using them. It is not very interoperable between all these different systems. If you want to do an optimum partition, you need to use a technique known as a mesh TensorFlow. But if you want to probably use a all-reduce technique, then Horovod provides the best system. So how can you combine all these different technologies in a single solution? Right? And last but not least, even the existing solutions sometimes have deficiencies. For example, you may run into heterogeneous models where some techniques are only working well for a part of the model, but not for the entirety of the model. And also sometimes there are specific characteristics inside the model, such as sparsity, which can be hard to deal with by a general purpose system. So in order to bring a universal and more convenient and generalizable solutions into distributed machine learning, I guess one need is to start developing a universal representation of the distributed machine learning strategy. And here I make a proposal. Here is an example of a strategy which consists of a collection of tuples. They could be specifying how to make partition, how to choose the system architectural topology, how to develop a bridging model between different nodes, how to compute and pass the messages, and also how to aggregate the messages. Just to give you a more concrete example, a parameter server can be realized by making instant instantiations of all these different aspects in the strategy to have a rigorous definition. And this is a graphical example of how a parameter server look like under such a uniform definition of the parallelization strategy. And here is a different architecture called all-reduce. You can see the differences between this one and that one could be just within a subset of the aspects. In here, the topology chose a ring structure, and previously it is a star structure. But you can use the same bridging model, and you may be able to also use the same partition of the model or the data and so forth. Right? So that suggests that the different strategies are not entirely different. Some parts may be reusable. If you nuclear it and make them a standardized building block, then there is a possibility of assembling a strategy just from those standardized spec instances like this. You begin with a computing infrastructure and a model design, and then you just navigate through this matrix of aspect instance choices, and then you stitch together, a collection of tuples, and then you come up with a strategy. So this is the idea behind a standardization of model parallelization and data parallelization and other type of parallelizations. When you are having various different type of models, or maybe even a model with a very heterogeneous data structure, then what you can do is to hopefully have a system automatically picking all these different components and come up with a strategy composition. So this is the idea behind what we would like to call a compiler, for machine learning distributed strategies. And in our recent work, we implemented such an idea called a strategy builder, which basically take the input as a model representation and the resource representation, and go through this building process and come up with a very optimized code to realize a distributed machine learning strategy. These components can be pre-made, or if you don't find what you need, you can customize it using the standard wrapper to deposit it into the library. And at the end of the day, you can start composition. So how to automate composition is also a very interesting strategy, because some advanced models like a big transformer may require different sub-strategies for different parts of the model. So therefore, one can benefit from a definition of a cost model in terms of the performance of the strategy. And therefore, you can build a model-based optimization procedure or use a strategy simulator to pick the best strategy automatically if you're rather not doing it manually. So that's how, at the end of the day, the system look like. It will take model representation and the computing resource representation, go through different types of strategy builders, and then provide an intermediate representation of the strategy specification. And then the system representation can accommodate not necessarily homogeneous, but also heterogeneous structures. For example, you can use a parameter server to handle the bottom layer of the neural network where parameters are very dense. And you can use a reduce to handle the top part of the neural network where the parameters are very sparse and so forth. So this is to contrast a traditional approach that we are doing now, where your system configuration and your model enters a black box and then come out with a homogeneous design of the distributed strategy, which has to be used all over a big model, which is obviously suboptimal. So here is a comparison of the AutoDisk technology that I described versus the bespoke distributed machine learning based on either specialized system artifacts or hand-tuned strategies. And you can see that in different types of deep learning models, the AutoDisk technology does have an advantage in all these cases by saving time, sometimes up to 60% better in terms of goodness. Then, let me jump into the next aspect of cost saving issue, which is how to schedule multiple tasks or even within a single task of computing. Again, back to our distributed learning algorithm. We started off by, looking into the data. And then one thing we often do is to start partition the data into mini batches, and they got deposited into different computing nodes, right? And then, a gradient or some type of update will be computed. They get averaged or aggregated, and then they get sent back to every node to have an update. Then this whole thing repeat. Therefore, two critical, tuning knob or maybe design space that people could leverage to either improve in the performance or do a bad job is to choose the ideal batch size and also the optimum learning rates. It turns out that this is not very easy because empirically people observe that deep learning training scale not so nicely, in fact, sublinearly to the performance. When you increase the number of GPUs into your system, you don't get that kind of a good throughput or results you expected in terms of a linear return, right? And therefore, what people do is maybe they suspect, maybe my batch size is too small so that I didn't make optimal use of every node. Why don't I just increase the batch size? It turns out that even if you increase the batch size, you still don't get perfect linearity. In fact, sometimes when the batch size become too big, you get a adversarial results where the results are worse than the smaller size. So here I want to say a few more words about the statistical efficiency, and the impacts of the batch size beyond the throughput. It is known that the statistical efficiency does not go with the batch size very linearly, because your learning rate and also the quality of the gradient really resulting from the batch could directly impact the statistical efficiency. And this is basically the gap that people empirically observed between a perfect statistical efficiency as a function of the batch size versus what you actually get in practice. And the gap is the actual computing you have to pay to train without a good return. Right? So just to sum up, when you change the batch size, you could increase the system throughput sometimes, but at the cost of dropping statistical efficiency in most cases. Therefore, there is an optimal sweet spot where you want to find to make the training performance ideal. But unfortunately, as you are moving along the training, even the size or even the position of this optimal spot itself is also changing. Therefore, at different stage of the training, your ideal batch size is also different. So all this actually points to a fluid resource requirement, which could compromise your system's utility. You have to basically prepare for the worst case scenario in your system resource allocation to adapt the peak need. And then when the peak is gone, your system will be underused. So we looked into this problem from a more theoretical perspective, and we found that it may be beneficial to go beyond just optimize throughput in our machine learning distributed computing as we do oftentimes, but to look at a new metric which we call goodput. The goodput is a new definition of the system performance that combines the system throughput with the statistical efficiency. And each of them could be parameterized with system free parameters so that you can start to model the throughput and the efficiency. So I want to say a few words here. For example, here is a particular formula you can use to model the system throughput. And here, the gamma is a learnable parameter that you can train on the observations you had of the existing throughput as a function of your system resource. And as the graph on the left show, this model is fitting the system throughput quite nicely, which means that you can actually predict the throughput ahead of time when you want to deploy or withdraw resource. Likewise, you can also model the statistical efficiency, using a parametric approach. This particular parameter here is reflecting the magnitude of the preconditioned gradient noise scale, which is often reflecting, the amount of statistical efficiency you are going to get. And once again, we see that with a bigger, batch size, sometimes we have a drop in the statistical efficiency, which validates, our empirical observation. And also the model can fit the real actual, statistical efficiency quite nicely, which, make it, useful for making predictions. Now, knowing the, being able to predict both throughput and the statistical efficiency really helps a lot when you want to come up with the ideal allocation scheme for resources. we begin with the given amount of hardware and also the computing task, which can be in the multi-tenant setting, meaning that multiple users are training multiple models. And then what you do is to use the model I just described to make a prediction of the job scalability, given different resources and different batch sizes. And then you aggregate all these predictions from different users and different training tasks to have a global optimum resource allocation scheme, okay, based on all these predictions and based on the good metric. And then you go back and reallocate resource. Therefore, you can see that this scheme is not just elastic or adaptive. We call them co-adaptive because you are simultaneously adjusting the resource and also adjusting the training procedures so that they can lock hands in hands to achieve optimal performance. So this system is called AdaptDL, which was recently published at OSDI. And here again is a comparison. You can see that the AdaptDL is achieving 2 or 3 times faster training time than existing systems or hand-tuned systems, where the hand-tuning is really taking advantage of being a single job and also having a lot of special knowledges about the work. One more thing that I want to mention before I wrap up is the task of tuning, which also plays a big role in making the machine learning costly. There are a lot of things in deep learning that we need to tune, as we all know, right? For example, the hyperparameters in those models, the neural architectures in the deep learning models, and also the system resources I just mentioned, right? So all these can be subject to change, when you change certain type of parameters. And typically what people do is to hand tune it, based on a lot of experiences, or maybe just based on an ad hoc technique. So our goal is to ask, is there a way to more principally and also automatically improve both intrinsic and extrinsic metrics? And maybe you also want to do it automatically because these tasks are highly demanding and also time consuming, right? So one approach I want to introduce here is called black box optimization. So black box optimization is a technique where you don't actually know the function you want to optimize, but you can query it. And then you can learn a model for the return and also for the uncertainty, and then accordingly query next time or choose the best strategy. So this scenario is a perfect fit for the type of tuning that I mentioned in our deep learning training tasks. And here are some examples of this technique being used. So let me say a few words about how this black box optimization can be realized and designed. First of all, we need to begin with a search space, for those parameters. It could be a continuous space of the hyperparameters. It could be a discrete space of the model architectures. And then you need to also define clearly what the query means, which in our case is the task of training a model. Then our objective, of course, is to achieve a maximum, say, performance, or lowers the cost in the training, right? And typically, how people do those search, well, what we often see are either a grid search in one dimension or high dimension, or maybe random search, and sometimes a genetic algorithm could be used. What I'm going to talk about is an approach called probabilistic Bayesian optimization, which is an instance of the model-based approach because it gives you a lot of appealing features in terms of cost saving and in terms of predictability. Here is a high-level picture about model-based optimization using the HPO as an example. We begin with defining. Our goal is to use a probabilistic acquisition model to intelligently plan queries and then perform efficient optimization, right? So this probabilistic acquisition model is essentially, a distribution of different scenarios of query and rewards. Okay, you can see all these curves. So it is a Bayesian prior, for the model. And then there is also an acquisition function, which is taking advantage, of the uncertainty modeling resultant from the acquisition model, and then calculate a utility of each query, taking into account both the return of the intrinsic value of the training, and also the amount of uncertainty you have to experience in using this query. Just a few more words about this acquisition function. Oh, by the way, both the acquisition function and also the acquisition model can be simultaneously learned using a nested iteration loop, right? You put the acquisition function inside the learning procedure of a probabilistic acquisition model, and then you are going to use a type of a reinforcement learning type of dynamic to query and creating the Y return, and then you add this one more data point to improve your estimation of the probabilistic acquisition model, and so on. The acquisition function is the key of informative and accurate prediction of the utility of the query. So here is an idea in defining the acquisition function. As I said, the probabilistic acquisition model is modeling the uncertainty of the query and the return match, right? And there are many of these possibilities. And therefore, this defines a posterior distribution, of the function of query and return. And you can basically optimize, a collection of samples from each of these from this posterior, so that you can get an optimum query point, for each of the instance of the posterior of the probabilistic acquisition model. And so the optimum query points itself becomes a set reflecting uncertainty. And then you can now define which one is best by doing the following thought experiment. So in your current estimation of the acquisition model, you get this collection of optimum query points, which has a disperse. You can calculate the entropy over that. And then if you choose one of the points or choose an interpolation of the points and generate one more data into training the acquisition model, you will have a new posterior for the acquisition, which actually has a different level of entropy. So the difference of the entropy, which models the kind of captures the information gain you have as a resultant of the query, could be used as a definition of the acquisition function. Okay. So use that, we can now implement an automatic program to do HPO. And here is a panel of the comparison of the results. You can see that across different choices of the models, our approach based on model-based optimization, it's not always the best, but it's consistently among the one or two bests, in different HPO strategies. And the same technique, MBO, can be used not just for NAS, for HPO, but also for NAS. All you need to do is to now define some kind of a distance functions between different model architectures, such as using a optimum transport function. And then your model can be now projected into a points of the search space. You can also define another neural network model, a Bayesian neural network model, to model the probabilistic acquisition model itself, so that you can define multiple objectives, not just a single one, such as computational cost plus performance of the model and so forth. And obviously, this technique can be also used for resource scheduling optimization. So now, before I wrap up, I want to maybe make a quick observation. So we've already seen that all this parallelization, scheduling, and tuning technique I just talked about could be realized through a pretty sophisticated and automatic system. One commonality they all have is that each of them is based on a model-based approach. Either model the utility of a distribution, the utility in terms of a good put, of job scheduling, or utility in terms of the uncertainty and the rewards, over an acquisition model. So that highlights the need of having, a mathematical understanding of what we are doing in deep learning, so that we can predict, the cost and also the rewards. Right. So that leads to me to conclude this talk by introducing, a latest result we had toward this direction: how to understand, deep learning or machine learning training and design in the principled and a unified way. So cost conscious they are really were asking for more principled and predicted deep learning. Making the task predictable really, can not only, save you cost, but also can improve, the result to value or the time to value kind of iteration. Without that, you are really looking like doing the alchemist experiments. You mix everything together. You put, I don't know how many transformers together into, or attention has together into big transformers. And then you actually have a little idea about the cost of training. But having the principles behind it is like you are now doing chemistry using a periodic table. You can kind of have a sense, about what, utility and cost, entails. Right? We're not there yet, but hopefully there will be more attention into this direction so that we can build on this knowledge to productionize, chemistry, or in this case, deep learning in a more systematic way. So back to our machine learning and the deep learning world, we are now still in a universe of many, many different artifacts of algorithms and heuristics. And that directly already point to one difficulty we already see, which is that to compute, for example, this update is going to be very difficult, and thereby, optimizing batch sizes, learning rate is almost impossible, right? Therefore, you can only do the kind of optimization I just mentioned for a few well-known models, but not too many. So there may be a need to develop a standard model that could cover as many as possible our current instances, or maybe even future instances of machine learning and deep learning models. And here is a proposal of such a model, which we call the standard equation. So it contains 3 parts. The first part is an expectation of what we call the feature or experience function over, the distributions to be learned for the data. And this experience could include not just the data examples, but also many other complex experiences, such as logical rules, such as rewards, such as adversarial experiences. And in our paper recently published, we have specific mathematical formulas to show how to encode these different type of experiences. The second term is called divergence term. It is kind of like the likelihood of target objective that we use in machine learning, which defines a mechanism between the teacher model and the student model so that they can get close to each other. So this is the driver of the iterative program, which tells you the fitness of the model being trained. It could be a cross entropy, Jensen-Channel divergence, or other type of divergence measure. And the last term is called uncertainty term, which governs, which is a self-regulation term to govern the amount of uncertainty, resultant inside your model. Right? It turns out that by plugging in different instantiations of these 3 terms, you can recover most of the well-known algorithms nowadays. Just like this tree is showing, it is using the standard equation to unify many existing learning algorithms and paradigms. And here is just a table showing you how these equation instantiations look like, and how this small number of hyperparameter should be instantiated. So what's the utility of that? Obviously, the standard equation, in my opinion, provides a very straightforward blueprint to do more complex multimodal machine learning, say from all experiences. For example, what if you are running into experiences of all this kind? You have not only data, but also you are interacting with the environment, and you are getting rewards by interacting, and you also have a knowledge graph setting up constraints. So in the case of having a standard equation, what you do is to now develop a linear combination, or maybe using a kernel trick to have a nonlinear combination of all these experiences together, so that using the same standard formula, you can seamlessly learn with multiple experiences jointly. So the standard model also provides you maybe a potential to develop a master algorithm, regardless of what learning paradigm you are actually instantiating, because in the root, their appearances and mathematical form are symbolically identical to each other. So here is an example of how this master's algorithm look like. Right, it is look like an EM algorithm or a teacher-student algorithm, where in the E step or in the teacher step, what you do is to combine knowledge from the experiences with the current version of the teacher model, and then in the M step or the student step, you try to draw the student closer to the teacher so that you update your current model to be learned, and then you iterate. There could be many ways of making this approach, more expressive and more powerful by introducing advanced techniques such as, kernel tricks, such as proximal gradings and so forth, which I'm not going to have time to cover. And also having this standard equation is providing a very clear roadmap to design data-centric principles for compositionality inside the machine learning model. For example, you can come up with Legos, which are designed around different building blocks, in the standard equation, such as the different instantiations of the experiences and the losses and algorithms. You can use a data pack that is a data frame universal across all these different Legos, so that you can, avoid the complexity or the tediousness of, doing data cleaning or data reformatting across different parts of the model. And then this assembly line enabled by our recent software package Forte is allowing you to wrap, either homemade or standard library functions and APIs, into a universal interface so that they can be combined like this to come up with a complex design. And that combination in a systematic way also make it easier for, say, tuning algorithms, for resource schedulers, and also for automatic distributing algorithms to start understanding the work better and then do the optimization of the resource and work. So to wrap up, I talked about a number of directions into understanding, predicting, and mitigating the cost of deep learning. And along with that, we developed some mathematical formula for each of these subtasks, and also a standard model that provides a blueprint for designing complex machine learning models, for real-world applications. The softwares I just talked about are all deposited, published in this open source consortium called Castle, which has a number of existing implementations already, alongside with the paper that is published or in the preparation to describe their mechanism, principle, and also usage. Some of the papers were already receiving some good recognition, such as a best paper at the OSDI and a best paper in ACL, but I hope more results are to come. So I'm going to wrap up here. Thank you very much for your attention.
Thank you, Eric. Thanks for the great talk. So for the interest of time, we can take one question here. I see, Aaron, you post some questions on the chat. Why don't you unmute and go ahead?
Okay, I can do that. Thank you. Thank you, Eric. This was a fantastic talk. I'm familiar with some of your latter work from Jiting's talk here. So he's one of my colleagues now here at UC San Diego. So the main question I have for you is, where do you see the industrial landscape evolving? The Google and Facebook folks tell me they're working on new tools that supersede Facebook and TensorFlow soon. JAX is almost halfway there. Do you see them open sourcing some of their scalability and parallelism techniques that they use internally that they're not open sourcing? And secondly, I see the homogenization claim that the Stanford faculty are making. I'm a little suspicious of that. Do you see that happening?
Well, you probably, the Google folks are in a better position to ask whether they open source or not. I wish they could. I think, the trend is that we want to, open source all this technique for a better exchange. But on the other hand, the position taken by Google and Facebook versus the position taken by, researchers like us can be different, because in their hand, they have resource and data, and they may be less sensitive to the cost issue. And but for the researchers, we are really limited by the cost bottlenecks. So I hope that on the research side, we should develop some kind of autonomy and less dependency, on those big companies' resource in terms of defining the agenda and also the style of the work, so that we can have more space to innovate. Because if everybody is go toward the path of gigantic big models, in a sense, there is a bottleneck due to policy or other type of business operation or company strategy, which could create kind of challenges, additional challenges, and maybe limitations of academic research.
Got it. Thank you. Totally agree with that.
Thank you. One of